All right, so we're going to go ahead and continue looking at example 3 where it says find the volume of the solid whose base is bounded by the lines f of x equal to 1 minus x. So I'm going to go ahead and draw that line in red. Okay, so that has a y-intercept of 1 and a slope of -1. The function g of x, which is equal to x minus 1, so I'm going to go ahead and draw that line in green. So that has a y-intercept of -1 and a slope of 1, and the line x is equal to 0. So we are talking about that highlighted area as our base, and whose cross-sections perpendicular to the x-axis are semicircles with a diameter on the base. So when I draw the cross-sections perpendicular to the x-axis, they're going to be semicircles that are like popping off the screen out at your face. Okay, so I'm going to go ahead and draw the cross-sectional shape over here. Now, when we look at the thickness of that cross-section, that is a change in the x direction. So we know our volume here. We are going to be integrating with respect to x. Okay, so that's the thickness of our cross-section. Okay, so the measurement that we know in regards to the semicircle is the diameter. So the diameter is going to be the length of the black segment, which is going to be the top function 1 minus x, minus the bottom function x minus 1. And when we simplify that, we get that to be 2 minus 2x, which we can rewrite if we factor a 2 out as 2 times the quantity 1 minus x. Now, ultimately, what we're going to need to find is the area of the semicircle, which is 1/2 the area of a circle. So it's 1/2 pi r squared. So we have to take that diameter measurement that we calculated and use it to calculate the length of the radius. So the radius is going to be 1/2 the diameter. So the radius is going to be 1 minus x, which is going to make the area of the semicircle pi over 2 times the radius, which is 1 minus x quantity squared. Okay, so I'm going to take pi over 2, that factor, and pull it out front of the integral. And then we are integrating between 0 and 1. And then we are integrating the function 1 minus x quantity squared with respect to x. So that integral expression is going to give us the volume of that solid. Okay, with number 4, the directions there ask us to find the volume of the solid whose base is the region between y is equal to x and y is equal to rad x, and whose cross sections perpendicular to the y-axis. Okay, so that's new. We got to think about what that means in a second. Whose cross sections perpendicular to the y-axis are rectangles whose height is 7 times longer than the base. Okay. So again, we want to draw ourselves a diagram modeling this. So we have the line y is equal to x, which is going to look like this. And then we have the curve y is equal to rad x, which is going to look like that. And we're going to draw our cross sections perpendicular to the y-axis. Okay, so my cross section is going to be that segment there in red. Now, when we look at the thickness of that cross section, the thickness of that cross section, the thickness of that thin strip is a change in the y direction. So that means that when we calculate volume, we are going to have to integrate with respect to y. Okay, So that tells me a couple of things. Number one, it tells me that when we set up our integral, our limits of integration have to be written in terms of y values. And it also tells me when I integrate my function has to be written in terms of y values as well. So to get the function written in terms of y values, we're going to take each of the equations and solve them for x. So the line y is equal to x, when I solve for x, that's x is equal to y. And when we take the other equation and solve for x, we get x is equal to y squared. So x is equal to y is the line. X is equal to y squared is the curve. Okay, so what we want to do is we want to take the cross section and we want to draw it over to the right so we can determine what the area of that cross section is going to be. Okay, so the base length of that rectangular cross section is going to be the distance in between those two curves. Now, if we remember finding area with respect to y, the larger curve is going to be the curve on the right. So it's the curve that bounds the area on the right side. And the smaller function is going to be the curve that bounds the area on the left. And again, we want both of those written in terms of y values, okay? Which is going to make the base length, the curve on the right, which is y, minus the curve on the left, which is y squared. And then the height is 7 times longer than the base. So the height is going to be 7 times the quantity y minus y squared, which is going to make the area of that rectangle the base times the height. So that is 7 times y minus y squared, quantity squared. Okay, so if we want to calculate the volume, we're going to pull 7 out front. And then we're going to take the integral. Now, again, we want our limits of integration written in terms of y values. So when we look at the y values that bound that area, it starts at the y value of 0 and ends at the y value of 1. And then we are taking y minus y squared and then squaring that quantity. Okay, and that's going to give us the volume of that solid. Okay, so we're going to move on to some like AP level examples next. So when I give you these questions, I want you guys to work these out on your own. So it's going to take like bits and pieces that we've talked about in this lesson and see if you can like figure out what method works best without being told what method to use. Okay, so I want you to try these on your own and then stop, and then you can check your answers at the end. All right, so number 1 says to find the volume of the solid obtained by revolving the region bounded by y is equal to 2x minus x squared, x is equal to 0, x is equal to 2, and y is equal to 0 about the line y is equal to -2. Okay, so we want to have like an image that we can refer to. So the function 2x minus x squared, that's going to be a parabola opening down. That's going to have x-intercepts at 0 and 2. And then the vertex is going to be at the point 1, 1. Okay, so graphically, the function looks like so. And if we're taking the region bounded by that curve, x is equal to 0, x is equal to 2, and the line y is equal to 0, so the line y is equal to 0 is the x-axis. That right there is the area that we are going to rotate about the line y is equal to -2. Okay, so when we look at this, we see that there is a space in between our area and the line that we are rotating about. So we are going to use washer method to set up our integral here. So when using washer method, we go from the line that we are rotating about. We're going to draw a thin strip perpendicular to that line. The thickness of that is a change in the x direction, so we know our integral is going to be written in terms of x. Okay, so we're going to take pi times, we're integrating, like the x values of our area lie between 0 and 2. And then we're going to take the longer radius squared minus the shorter radius squared. Okay, well, the longer radius is going to be the distance from the line we are rotating about to the curve that's the furthest away. Okay, well, we know the distance from the curve to the x-axis is the function value, so that's 2x minus x squared. And then what are we doing to that distance if we're rotating about the line y is equal to -2? We are adding 2 to that length. Okay, so that's going to be 2x minus x squared plus 2 quantity squared. And then the shorter radius is the distance from the line we're rotating about to the curve that's the closest. And the curve that's the closest is actually the x-axis. And that distance is going to be 2. Okay, so you can either write that as like 2 squared, or if you want to write that as like the function, which is 0 plus 2 quantity squared, either one of those is okay. Okay, I'm just going to write it as 2 squared because I think that's how you're going to want to evaluate this. All right, so that right there is going to give you the volume of that solid. Now, again, if you wanted to evaluate this by hand, like you'd have to expand out 2x minus x squared plus 2 quantity squared, and then combine like terms subtracting the 4, and then integrate that result term by term. Okay, for number 2, the directions say to find the volume of the solid that results from rotating region R. So region R is that shaded region in black about the line y is equal to 1. Okay, so again, find the volume of the solid that results from rotating region R around the line y is equal to 1. Okay, so let's take a look at this one. What we're going to want to do for this one here is we actually have to break this up into 2 volumes. And the reason being is that the function that bounds the area between a and 1 is the function y is equal to f of x. And the function that bounds the region between 1 and 2 is the function g of x. Okay, so we have to set up separate integrals to calculate those respective volumes. Okay, so again, there, and I'm going to do this in the navy blue. Okay, so there's a space in between the line that we are rotating about and our area. Okay, so for both of these, we are going to want to use Washer method to calculate volume. Okay, so when I use Washer method for that first area, the volume is going to be pi times the thickness of both of those cross sections are a change in the x direction. So we're going to have to integrate both of the integrals with respect to x. So the first integral's area is between the x values of a and 1. And then we want to determine the length of the longer radius. Okay, so the longer radius is the distance from the line we're rotating about to the curve that's the furthest away. So the curve that's the furthest away is the line y is equal to 0. So the distance in between the line that we're rotating about and the x-axis is 1. So that's going to be 1 squared minus The shorter radius is the distance from the line that we are rotating about to the curve that's the closest. Okay, well, we know the distance from the line we're rotating about to the x-axis is 1, and we know the distance from that curve to the x-axis is just going to be the function value f of x. So the distance in between the line that we are rotating about and that curve is going to be 1 minus f of x quantity squared. Okay, and that right there is going to be our shorter radius, which we're integrating with respect to x. So that's going to give us that first volume. Okay, and we're going to have to set up a second integral expression to calculate the volume when the second area, so the one that I've highlighted here in light blue, when that is rotated about the line y is equal to 1. So again, the volume there is going to be pi. This time we are integrating from 1 to 2. Again, we're using washer method because there is a space in between our area and the line that we are rotating about. So the longer radius is going to be the distance from the line that we are rotating about to the curve that's the furthest away, okay, which is again going to be 1, which we have to square that radius, minus the shorter radius is going to be the distance from the line that we are rotating about to the curve that's the closest. Okay, so again, we know this entire distance is 1. We know the distance from the function to the x-axis is just the function value g of x. So this distance right here in yellow is going to be the whole thing 1 minus the function g of x. Okay, so this will be 1 minus g of x, quantity squared. And then again, the thickness of the cross-section is a change in the x direction. Okay, last example, and I think this one should be the hardest one. Okay, so number 3 says that a region R is bounded by the curve x is equal to y squared minus 1 and the y-axis. And then the question asks, what is the volume generated when region R is rotated about the y-axis? And I ask you to please set this up in 2 ways. Again, I want you to pause the video, give this a try to set it up 2 different ways, and then we'll take a look at how we can find the volume together. Okay, so when we look at x is equal to y squared minus 1, that's going to be a parabola opening to the right that has a vertex at the ordered pair -1, 0. Okay, so graphically, that function is going to look like this. So if we want to take the area enclosed by that curve and the y-axis, that is going to be the area of that shaded region in yellow. Okay, and we're going to rotate it about the y-axis. Now, there are 2 ways for us to set this up. Okay, the first way is, for me, I'm going to use cylindrical shells. Okay, so when I do this with cylindrical shells, I'm going to draw my thin strip parallel to the line that we are rotating about. Okay, so that right there is my thin strip. Now, the thickness of that thin strip is a change in the x direction. Okay, so what that means is I have to get my equation, so my function, as well as my limits of integration written in terms of x values. So when I take this equation, x is equal to y squared minus 1. I want to solve this equation for y, so we get y squared equal to x plus 1, which is going to make, when I take the square root of both sides, the absolute value of y equal to rad x plus 1, which is going to make y equal to plus or minus rad x plus 1. Okay, so the positive radical is going to be what gives us the top half of the parabola. Okay, so that gives us this top half of the parabola. And the negative radical is what gives us the bottom half of the parabola. Okay, so again, the top half of the parabola is the positive rad x plus 1, and the bottom half of the parabola is going to be the negative rad x plus 1. Okay, so I'm going to erase the work that I did over here, just so I have room to set up the integral. Wow, this is taking a long time to erase, sorry. Okay, so if we want to set up volume using cylindrical shells, so our volume formula is going to be 2 pi. Again, the thickness of our cross section is a change in the x direction, so we're going to be integrating with respect to x, which means my limits of integration have to be written in terms of x value. So when we look at that area, the smallest x value that bounds the area is -1. The biggest x value that bounds the area is 0. Okay, now the radius is going to be the distance from the line that we are rotating about to the cross section. Okay, so when I take the distance from the cross section to the line that we are rotating about, we said that that distance is going to be the absolute value of x. And since our graph lies in quadrants 2 and 3, we know the x values are negative in those two quadrants. So when we take the absolute value of something that's negative, we take the opposite of that quantity. Okay, so to ensure that that radius is a positive length, we have to take the opposite of that x value. And then we are going to multiply that by the height. So the height of the cross section is going to be this segment there in light blue, which is just the distance in between the two curves, which is the top function, rad x plus 1, minus, I'm sorry, I'm running out of space, minus the bottom function, which is negative rad x plus 1. So I can make this volume here then 2 pi times the integral from -1 to 0 of negative x, and then rad x plus 1 minus negative rad x plus 1 is going to be 2 rad x plus 1 dx. And then I'm going to pull the coefficient -2 out front. So the volume here is going to be -4 pi times the integral from -1 to 0 of x rad x plus 1, which we're integrating with respect to x. Okay, so that's the first way for you to set up an integral that calculates volume, okay, using cylindrical shells. Okay, we're going to do this a second way, so I'm going to draw the graph again down below. Okay, so graphically, the function looks like this again. It's a parabola opening to the right. We're rotating this about the y-axis. And again, this is the area here that we are rotating about the y-axis. Okay, now the other way that we can do this is if we are taking that area, rotating it about the y-axis, we can actually use disk method with respect to y. Okay, and again, the reason that I can use disk method is my area lies flush against the line that I am rotating about. So there's no space in between that area and the line that I am rotating about. So if I draw my cross section for disk method, I want to draw it from the line that I'm rotating about perpendicular to that line. Okay, so when we look at the thickness of our cross section there, that thickness is a change in the y direction. So we know volume we're going to want to integrate with respect to y. Okay, because again, the thickness of our cross section is a change in the y direction. Okay, so if I use disk method, I'm going to pull pi out front. If we're integrating with respect to y, we need to look at the y values that enclose the area. So the smallest y value that encloses the area is -1. The biggest y value that encloses the area is 1. And then we want to determine the length of the radius. Okay, so the length of the radius is going to be like the length of this segment here in light blue. That's the distance from the line that we're rotating about to that curve. Well, again, the way that we determine that distance is it's going to be the function that bounds the area on the right, which is 0, minus the function that bounds the area on the left, which we have to write in terms of y. So that's going to be minus the quantity y squared minus 1, quantity squared. Okay, so volume here would be pi times the integral from -1 to 1. If I distribute the negative across both terms, we get 1 minus y squared, quantity squared, which we're integrating with respect to y. Okay, and that right there is going to give us the volume utilizing disk method with respect to y. Okay, so wow, that was a big lesson. There's a lot of stuff. Again, with your homework assignment, you guys are only going to do disk method and washer method for the homework that's due this week. And then I'm going to have you do the cylindrical shells homework for next week. Okay, so the 6.2 homework is due this week. 6.3 is due next week. Be on the lookout for some AP problems with area and volume. I'm going to post those for you guys to work on in class on Monday. Okay, so hope you guys have a great rest of your week, and we'll see you soon. Take care.